Now let's dive into combinations. So the way I like to remember these phonetically is that a permutation is used when we're looking at a podium finish. In other words, first place versus third place does matter. Versus a combination, if we're appointing people to a committee and all the positions are the same, the order doesn't matter of which, people go up on a stage or whatever like that. It's a committee. There is no order. Now, if order doesn't matter, I want to ask you intuitively, do you think a combination will be larger or smaller than a permutation given the same set of circumstances? So if we're looking at 7 athletes into 5 positions, do you think there's more ways that could occur if the order doesn't matter, or more ways if the order does matter? Well, as we're going to see in this derivation, a permutation is kind of like a combination, but it also accounts for the ordering of those objects. So a permutation will always be equal to or greater than a combination. Because not only do we have the base, but then we're multiplying it by a factor to include the way that those could be ordered within each other. So, and this is the main takeaway of the video. A combination is just a permutation divided by the number of ways that it can be uniquely ordered. In other words, if you can remember this, you'll never have a problem with combinations and permutations again. So let's look at that example of voting 5 people on to a committee out of 7 possible candidates. So let's jump back to the very beginning of our general permutation formula, where it's n factorial. Now we need to modify this number from here to meet our specific criteria. Our first criteria is that there's only 5 committee positions out of 7 candidates. The second criteria is that we don't care about order, and that's the definition of a combination. So let's account for this first thing, and that's going to be using this formula. We're going to divide out the number of ways that those last 2 candidates could order themselves because we don't care about them. And so this right here is our permutation formula for when there's less positions than there are competitors. Now the next thing we need to do is account for the fact that the order doesn't matter. And how do we do that? Well, a combination is equal to a permutation, and we divide out the number of unique orders. And this is why we see that a combination will always be less than or equal to a permutation. Because when we divide by 1 over factorial, that makes the whole number smaller. The case in which it could be equal to is this number where 1 or 0, because we know that these hold true, and so we just be multiplying by 1 over 1, which is equal to 1. And so combination would be equal to a permutation in that instance. Now, let's write the general version of this. So we know that we started with our vanilla permutation. We divide out the number of ways that the remaining competitors can finish. We don't care about them. And then we also divide it out by the number of ways that they can be uniquely ordered. And so this is why I said that you'll never get combinations and permutations mixed up again, because it all derives from this one simple equation, n factorial, and then we just account for the specific situation we're dealing with. If we don't care about the remaining items, boom, divide them out. If we don't care about the remaining items or the number of ways that they can be ordered, boom, divide it out. Thanks for watching, and I hope this made a little bit of sense to you. Definitely check out my other videos on probability statistics, such as my cumulative distribution function videos. Thanks for watching.